just because of logistics today, we're going to kind of split the class. And so if you are watching this, that means you're ready to do some friction analysis, the lab analysis, learn a little bit about friction, and then do some problems. So at this point, we've finished the front of the lab sheet, and hopefully you have already taken data and graphed your data. And I'm hoping that we've checked in by this point and you've also got some lines, so some best fit lines. So if you have not yet drawn a best fit line on your graph, you're going to get a ruler, because I don't want you to play connect the dots, but I actually want you to get a ruler and find a best fit line for both the kinetic friction, which was the average one, and also the static friction, which is the little peak that we found. Okay, so pause the video if you need to, find or draw those lines, and then on the new piece of paper that I've just handed out or you've come up to get, the follow-up questions, the first thing that you need to do is to find the slope of each of your best fit lines. So we've done this a couple of times, but just a couple of reminders, because I am going to grade this as lab credit. So I want to make sure that you're going to earn your credit. Okay. A couple of things. Make sure that when you find the slope, the points that you have are not data points, but they are points on the line. So you need to look at your line, find places where your line crosses hash marks, and then go ahead and find the coordinates for those points. So in the little chart below, you're going to go ahead and write down your X and Y coordinates. So X1, Y1, and X2, Y2. So you're actually going to write down numbers there and then calculate your slopes. So you're going to show me your work in the big box and then tell me your calculated slope with units, please, in the second box, in that calculated slope box. Once you've done that, if you have an opportunity, please compare very quietly, if you're in class right now, slopes with at least one other group, okay? The values don't necessarily need to be the same because you're using different situations, and that's fine. But really what I want you to focus on is which type of friction, static or kinetic, resulted in a larger slope for you and for your other group, and then give an explanation, if you can, for your findings from question 2. Okay, so the idea here is that we're kind of trying to start introducing the factors that affect friction. So we're going to do a few notes here, and you may want to write some of this down as well, just so that you've got it and it makes sense to you. Okay, so some information about friction. We've talked about it before, but just a couple of pieces. Okay, it is a force of a surface on the object. Okay, it always acts parallel to the surface, and it always opposes the motion of an object. The amount of friction that is involved in any system is dependent on two things. One of them is what you measured in your lab. You hopefully saw that the force of friction increased as you increased your mass. That's why you got a nice line. So one thing that we know is that the force of friction increases as mass increases. Now that's a little bit misleading, and in AP Physics we do some analysis with this, but really what it is that the force of friction increases as the normal force increases. For all of our situations, when you have just a box sitting on a horizontal surface, if Fg is pulling down and Fn is pushing up, if there are no other forces acting up and down, then Fg and Fn are going to be equal, right? And Fg is equal to mg. So for our purposes, when mass gets bigger, that means that the force of gravity gets bigger. And when the force of gravity gets bigger, it means that the normal force gets bigger. So the reality of it here is that the force of friction is dependent on normal force, okay? The other thing that the friction depends on is the types of surfaces that we have put together, okay? So we can talk about the slipperiness or the stickiness of those two surfaces, and that piece is called, and this is the big deal for today, the thing I really want to make sure you have gotten, the coefficient of friction. And this is a value that can be found experimentally between any two surfaces that interact. So if you think about something like a nice, like a bowling ball going down an alley, both of those surfaces are very smooth. And so the coefficient of friction is going to be very, very low. Okay. But if you think about like rubbing a piece of wood against sandpaper, that's a very, very high coefficient of friction because those two surfaces are very rough. Okay. So the coefficient of friction is basically the slipperiness or stickiness of two surfaces put next to each other or rubbing next to each other. So I'm going to write that down, the slipperiness or the stickiness. Oops, I did not spell that well. Let me try that again. Stickiness of two surfaces that are interacting. And the coefficient of friction is marked by a new to you letter, probably. It's a Greek letter. If you take a look up at the Greek alphabet that's up at the front of the classroom, you will see this letter. And the letter looks like this. And it's the letter mu. So in Roman letters, we spell mu, M-U, okay? So mu is the coefficient of friction. And for any situation, you've actually got two different values for mu. Mu sub s and mu sub k. All right, so mu sub s is the static frictional coefficient, and k is the kinetic frictional coefficient. So we're going to put all of this together, and we're going to get an expression for the force of friction. So the force of friction, just one second here. Okay, oops. The force of friction, maybe, is equal to mu times Fn. So again, Fn is the normal force. The higher the normal force, the higher the frictional force. That's what we found when we were doing the lab. That's why when you had mass down here, which was really just a way to look at force of the normal force, and friction, as the mass went up, the frictional force went up. So that's what that is. And then the coefficient is really what you found as your slope. In, again, kind of hiding in there. The coefficient is the stickiness or slipperiness of the two materials next to each other. So FF is equal to mu Fn, and that's true whether it's sliding or whether it's standing still. There are a couple of other little details there that I'm not gonna bother with, but that's what you need to know. Looking at the units for mu, if we divide Fn on both sides, we can get FF over Fn. The units of FF are in newtons because it's a force. The units of Fn are in newtons because it's a force. And so it's kind of funny, but the coefficient of friction actually has no units. It is a unitless quantity. It's just a ratio between two materials. Okay, so that's kind of an interesting thing. So you'll want to know this FF is equal to mu Fn. That's going to be something that we're going to use in the next little bit of what we do. So that's the short version of what you need to know about friction, okay? Again, friction is dependent on the normal force, and it's also dependent on the coefficient of friction between two surfaces. That's something that you can find experimentally. There are charts of that in places, but for what you need to know, just that it is. Also, one other little thing is that mu is generally less than 1. So it's a ratio that's generally less than 1. The higher the mu is, the more sticky the two surfaces are, or the harder it is for one to slide against the other. Okay, so that's the first thing that you need to know. I'm also going to walk through a problem with you, and the reason for that, I'm just going to go back to the sheet that you have. So this is the second part of the Factoring Friction Lab. After you've watched this video, you're going to also finish 2 problems that are from your book. Okay, I've broken down the problems into some nice charts just like we've done before, but I want you to just be kind of familiar with that, and you're welcome to use them or not. But those charts are there, and the reason that I'm telling you that is because I'm going to work through a problem right now that will help you with those. So I'm going to do problem. I'm going to scroll down here. I'm going to work on page 141, problem number 1, okay, to kind of help lead you through this process. Please make sure that you watch this. Please make sure you go through it with me before you do your problems from the book. Just, it'll make life much easier, okay? So I'm going to read the problem. You can also get out a textbook so you can take a look. A student pulls on a rope attached to a box of books and moves the box down the hall. The student pulls with a force. So I'm going to go ahead and just start out with some givens here. Maybe. Pulls with a force, Fa, of 185 newtons, okay, at an angle of 25 degrees above the horizontal. The box has a mass of 35 kilograms, okay, and it says the mu sub k, so that's the coefficient of friction, of kinetic friction, between the box and the floor is 0.27. So that's pretty low. It's a pretty smooth surface, it sounds like. The question asks you to find the acceleration of the box. So if it says to find the acceleration, that probably means that we're going to be able to, or this thing is going to be accelerating. So once I've got my givens, the next thing to do is to draw a picture. So I'm going to go ahead and draw my picture. I've got some forces acting, like the force of the earth on the box, Fg. Okay, I've got the normal force, the force of the surface or the force of the floor on the box. That's my Fn. I've got an applied force acting up at an angle of 25 degrees. I'm going to double check here. It says 25 degrees above the horizontal. So, yep, I'm good to go there. So there's my 25 degrees. Okay. And then it's talking about friction, which probably means there's friction involved. So I'm also going to draw my friction force. Friction is always going to act parallel to the surface. So this is the force of the floor on the box, parallel. So that's the frictional force. Okay, oops, and I didn't actually label this applied force here. The force of the student on the box. Okay, so that's my applied force. So now, just like I have in all of my other problems, I'm going to break this up into x and y. So I've got a force in the x direction. I've got a force in the y direction. And I'm going to break those up. So I'm going to go ahead and draw this triangle here. So this is my applied force. Fa, oops, x. And I've got Fay. Hopefully you're feeling like you've done this before a few times, because indeed you have. Fa cosine theta. And then we can figure out what those two values are. Okay. Once we've done that, we can go ahead and, just like you have done in the past, we're going to write down F-net equations in the x and in the y. The reason for that, ladies and gentlemen, is that we're trying to find acceleration. In order to find acceleration, we need to find the force of friction. Okay, so let's go ahead and write these out and see how we do. So F-net in the y direction, so we're going to look at everything that's acting in the y direction. So it looks like I've got a normal force acting in the y direction. I've got an applied force in the y direction. That one is positive, so I'm going to leave that positive. And I've got Fg. That one's pulling down, so I'm going to put a negative sign. Adding those three up, have to add up to 0 because the box is not going to accelerate in the up and down direction. Okay, so I can say that Fn is equal to, it'll be Fg minus Fay. Need to do some mathematics here. So we're going to have 35 kilograms times 9.8 meters per second squared minus, this is going to be Fa, so that's the 185 newtons times the sine of 25. You're going to get your calculator out. I'm going to get my calculator out, and we're going to do the problem. So 35 times 9.8 is 343. I'm going to subtract 185 sine 25 from that. And I got 264.82 newtons. So hopefully that matches with you. If it doesn't, let me know and we can go through it. And then we're going to do F-net in the x direction. So if we look at the look at the free body diagram. We're going to add up all the forces that are acting in the x direction. So I've got Fax, and I've got the force of friction. Force of friction is acting the other way. They are not going to add up to 0 because it says that it's got some acceleration, or it actually potentially has some acceleration. So I'm just going to write that as F net equals ma. So I know Fax, that's going to be Fa times the cosine of theta. That's what I got way up here, okay? And then I've got to figure out what my FF is. Now, I don't know what FF is for sure, but I recall from the conversation we just had that FF is equal to mu times Fn. So part of the reason I did this was to find my Fn. So now I can throw in my mu, which is 0.27, okay? And I'm going to multiply that by the normal force that I found, which was the 264.82. Oops, 0.82. And that will give me my frictional force. Okay, I'm going to take that and divide it by my mass, and that will tell me my acceleration. So I'm going to go ahead and do that really quickly just to make sure that we've got it all figured out. So Fa is 185, so 185 newtons times the cosine of 25 degrees. That's my Fa and the x. I'm going to subtract the 0.27 times the 264.82. So again, this is the coefficient of friction, and that's my normal force, which gives me my frictional force. I'm going to divide that by my mass, which was 35 kilograms, and that will give me my acceleration. So I'm going to plug in some numbers. Again, do it too so that you make sure that it makes sense to you. You're just plugging stuff in here. Some nice music while we wait. All right, divided by 35. So I got 2.7 as my answer, or 2.75 was with going out to the hundredths place, meters per second squared. So hopefully that made sense to you. If it went too fast, you can always go back. If something really didn't make sense, then let me know. Okay, we can talk it through. I'm happy to do that, but hopefully that helps. Now it is your turn. You've got 2 problems to work on the back of your friction lab, okay? These problems are due at the end of class on Wednesday, okay? So you've got lots of time to do that, but by the end of class on Wednesday, they need to be turned in. Thanks so much. Have a great day, you guys.